Hi guys, so we just started discussing a few Banach spaces, at the moment confined to sequence spaces. The first one was the LP space equipped with the P norm for any P from 1 including infinity. Those are Banach spaces. Then we looked at subspaces. So the first one would be that Z0n. That is a subspace of L infinity. It's in general not a subspace of LP, think about that. And moreover, equipped with the infinity norm, it's actually a Banach space. We showed that by, well, simply proving that it's a closed subspace. Then a further subspace of that one would be Z00n, which are sequences that sort of terminate, after some point. That is to say that have terms equal to 0 for all but a finite number of n. Equipped with the infinity norm, this is also a Banach space. This one, by the way, is a subspace also of LP, right? Because if your sequences have only finitely many non-zero terms, then of course all those series with the p's in it, they will be convergent, right? Okay, good. However, we showed it's a Banach space for p equal infinity, and now I will show that this is actually the only value for p for which it is a Banach space. In other words, we will now prove that Z00n equipped with the p norms and p different from infinity is not a Banach space. Okay, what we have to do is we'll find a Cauchy sequence which has a limit, but the limit is not in that space. Okay, so here's a candidate. Look at following sequence. So xn, xn1, xn2, so on and so forth. So what I'm going to do is it will be 1 over 1, 2p, 1 over 2, 2p, 1 over 3, 2p, is so on and so forth. And then the last non-zero term will be 1 over n to the 2p, and after that everything is 0. Okay, so this here, that is the nth slot, and that is precisely the index that is here indicated on the left. All right, by definition, by construction, this is an element of Z0n, right? Because, well, after finitely many terms, everything, the entire tail here, is equal to 0. Good. Now what we have to show is that this is a Cauchy sequence in the p norm. All right, so I look at then for any n above m. Okay, so what I have to do is I have to estimate xn minus xm in the p norm, and again, as usual, I will just raise this to the power p so that I don't have to drag around the roots. And then by definition, this is xnk minus xmk to the power p. But now look in the way it is constructed. Let me move this here maybe a bit further down. So if I have n bigger than m, so say here is n, and then m is somewhere here. If I subtract these entries, well, then I will subtract off precisely everything that is at m or to the left of it, right? And the only things that survive are in between. So this will be k from m plus 1 up to n. And then what survives? Well, it will be, well, these terms in the middle. So this will be 1 over k, and then to the power 2 and divided by p, but then everything raised to the power p. So this will just be k squared. Okay? And that, of course, is well, tail of a convergent series. So you just use the Cauchy criterion for series. As m goes to infinity, this one goes to 0. Right? So, in turn, xn in Z0n is Cauchy. Okay, it's a Cauchy sequence in that p norm. All right, but maybe I should write this in the p norm. Right? We have to be careful with what norms we're working here. Like so, is Cauchy. but well, I claim xn as n goes to infinity in p norm converges to the following object: 1 over 4 1p 1 over 9 1p 1 over 16 1p, and it doesn't terminate, right? So to find that limit or to get an idea for it, well, you just push the n all the way to the right, and then the first one will be 1, then this will be a quarter, and then a pth root, then 1 over 9 in the pth root, and that's precisely what is written here, and so on and so forth. Okay, so now this I claim, so now I have to prove it. Well, indeed, we have to estimate xn minus x in the p norm, say again raised to the power p. Now this is again as before the computation, everything to the left including n you subtract off, so this is just a series from n plus 1 all the way up to infinity, and then the same elements, 1 over k squared, and as n goes to infinity this will go to 0. All right, however, obviously the limit is not an element in Z0n because it doesn't terminate. All its terms are non-zero. Okay, that's why it's not a Banach space. Good. Still, final comment about this one, and I will put this on the exercise sheet. Z0, Z00n with the p norm is, although not a Banach space, it is dense in a Banach space. Dense in the Banach space LP with the p norm. P for, well, p away from infinity, and what happens for infinity? Well, then it's dense in some other Banach space, which is the one in the previous example, and this is dense in Z0n infinity. This will appear on the exercises, these two problems. Okay, good. All right, so as you can see, this business is extremely sensitive to whatever distance, whatever norm you put on your spaces. Sometimes then they happen to be complete. We had examples. Sometimes, well, it fails. To further emphasize this point, let's look at another example. So let's leave the discrete world and let's go to the continuous functions now. So let Z01 denote the vector space of f-valued continuous functions defined on the compact interval 0, 1 on the real line, and equipped with the p-norms, with the norm, the p-norms that we discussed in the first chapter on normed linear spaces. Up front for arbitrary p ranging from 1 all the way up to infinity. All right. Now, so in a way, these continuous functions, they are, well, continuous analogues of the sequences. However, they behave differently, right? So in the LP case, we found out, this was the first example, that for any p from 1 all the way up to infinity, that's a Banach space. Now here it's different. That guy, Z01, continuous functions on 0, 1, with these p norms is only going to be complete when p is equal to infinity, for no other values of p. Okay, let's write this down. Then Z01 with p norm is a Banach space only for p equals infinity. All right, so first, if p is different from infinity, remember, In the Hilbert space chapter, we looked at that space with the 2 norm, and we showed that it's not a Hilbert space, right? So, and if you carefully study that proof again, you realize we actually didn't exploit the fact that that norm comes from an inner product. We constructed a sequence of piecewise linear functions. So this was equal to 0, then straight line equal to 1, and as n became large in the 2 norm, that thing converged to a discontinuous function, right? That's why it's not a Hilbert space. Now, but that argument you can carry over to any p different from infinity. That's what I'm trying to say. So if p is in between 1, strictly less than infinity, simply modify our workings of the previous p equals 2 counterexample. You can take the same function, that same sequence of functions, and well, the only thing that you need is again Minkowski inequality, right? And then it goes through. All right, good. So the only thing now that I will prove is that, well, it is complete when p is equal to infinity. Okay, if p is equal to infinity, the situation is different, and then this, maybe for some of you this doesn't come as such a surprise. I will explain why. Let's first write, if p equals infinity, the situation is different. Why is it maybe not a surprise? Well, because in some module, maybe metric spaces, maybe some real analysis, you learned about sequences of functions or function sequences, and then there's at least 2 notions of convergence, which one of them is pointwise convergence, the other one is uniform convergence. Now, if you start with a sequence of continuous functions and that thing only converges pointwise, then in general the limiting function is not going to be continuous. It's different when you have uniform convergence, which is better because then the limit is continuous. And that's precisely what this statement here says. So that if you have a sequence of continuous functions and the convergence is the infinity norm, and the infinity norm is equivalent to uniform convergence, then it says here that space is complete, right? So that means that the limit is again a continuous functions. So if you're aware of this connection, then this is just paraphrasing here what you already know, and maybe you have already seen the proof of. Anyways, I will do the proof again. So let's start with a Cauchy sequence. Let Fn be a Cauchy sequence, and then again 3-step process, find a suitable limit candidate, show that it is continuous, and then prove convergence in the the relevant norm, right? So let Fn be Cauchy. Then for any fixed x in 0, 1 and all n, m, n. So very much like for the sequences when we had to carry around those double indices, here you have also 2, you got the n and the continuous variable x. That's the only difference. So what you do is you look at fnx minus fmx. Now you're going to optimize, so you take the supremum, so here since these are compact intervals, that's just the maximum, and yeah, but since it's a Cauchy sequence, this guy in infinity norm goes to 0, right? So fnfx for any fixed x is a Cauchy sequence of either real or complex numbers. Is a Cauchy sequence. And thus pointwise convergent, because the real number field or the complex number field is complete, and thus pointwise convergent. Okay, say fn of x goes to f of x for any fixed x as n goes to infinity. Okay, now we have to show, so this will be our limit candidate. Now we will show that it, well, it does everything that we want from it. So next, for arbitrary xy in 0, 1, so let's write down what it means to have a Cauchy sequence. Well, arbitrary epsilon, we can choose capital N, so that Fn minus Fm, there will be some cosmetic surgery here. I will work with epsilon over 3, and you will realize soon why I do this. It's not essential at all, because epsilon is arbitrary, but let's do it anyways. And so now you have here a sequence of continuous functions on compact intervals. Yeah, but continuous functions on compact intervals are uniformly continuous. So that means in the continuity definition, for any given epsilon, there exists a delta. That delta is independent on the points on which you zoom in. Okay, that's why uniform continuity. Okay, and also delta epsilon positive, so that, well, I can do it for any term in the sequence, but I will do it for this capital N. You will soon realize why. So this is also less than or equal epsilon over 3 whenever the x and y are sufficiently close, less than delta in distance. Okay, in turn, for any m exceeding capital N and x minus y less than delta, so I want to show that my limit candidate is continuous, so I should be able to make this difference arbitrarily small, right? Actually, that will prove uniform convergence, but which is even better, but in particular, not uniform convergence, uniform continuity, which is better than what we need, but still. All right, so how to do this? Well, now you insert those terms so that after application of triangle inequality, you have control over the various bits and pieces. All right, so the first one you introduce is this one, small n. So for any fixed x, as small n goes to infinity, that guy will go to 0 because of the pointwise conversion that we had above. Then the next one, you're gonna subtract small n with the capital N. That one you have control after you optimize it, so after you estimate it by the infinity norm of f small n minus f capital N, because it's a Cauchy sequence, right? So this is less than or equal than epsilon over 3. Now you have to switch from x to y, which you do like this. That guy you also know how to control because of the uniform continuity. That's what's also written up there. And then you count sort of down, maybe with m instead of n. This one, again, you have control after you optimize it with the infinity norm because you have a Cauchy sequence. And then the last one, which is this one, you have control pointwise as m goes to infinity in y because of the pointwise convergence. Okay, so let's write this all down. So you have f of x minus fn of x, and then, this one, less than, I said it in words, now I'll write it in yellow, less than or equal to epsilon over 3. Same here, and this one less than epsilon over 3, so 3 times gives you an epsilon. That's why you had this little cosmetic surgery there with the denominators, which are 3, and then fmy minus f of y. Okay, that's what you have. Good. So in the limit, right, so now we're going to do is, as usual, you push small n and capital M to infinity, noting that your left-hand side does not involve those quantities whatsoever, right? And so in the limit n m into infinity, using the pointwise convergence fn of x, f of x, we find that f of x minus f of y is less than epsilon when x minus y is less than delta. Okay, so this shows uniform continuity of the limit candidate, and thus in particular continuity on the closed interval 0, 1. Good. Now the only thing that remains to show is that the convergence to that f holds in the infinity norm. Okay. Finally, let epsilon positive be arbitrary, and n epsilon positive, so that, well, Cauchy, so fn minus fm infinity less than epsilon for nm above capital N, then for all x 0 n and any n m above capital N. As usual, you're not going to take the supremum up front. You first work in this sense for any x. You get control over this guy uniformly in x, and then you take the supremum. Very much like we did it for the sequences. Alright, so you insert this, fmx minus f of x. Then the first quantity here you optimize, you get the infinity norm of the difference fn minus fm. That difference is small. And the last guy, fm of x minus f of x, as m goes to infinity, notice the left-hand side is independent of m, it goes to 0, right? And since this holds true for any x in 0, 1, so you get that fn minus f infinity less than epsilon for all n above capital N. And that's precisely what you want. That yields the convergence to f of our Cauchy sequence in the infinity norm. All right, good. That concludes this example. Now, one more, which is, well, we already did all the relevant work for it. We're just going to recall it because we're going to use it very, very soon. So remember in the chapter on normed linear spaces, after we defined bounded linear transformations, we talked about the operator norm. And we proved that the vector space of bounded linear transformations from x to y equipped with the operator norm is complete when the space y with its own norm is complete. Now here we're just going to paraphrase this in the language of Banach spaces. That's all that I'm doing now. So let x be a normed linear space and, well, y a complete normed linear space, so a Banach space. That's the only thing that I'm doing. Banach space, then this guy Lxy with the operator norm is a Banach space. Okay, this was, if you go through the lecture notes, it is theorem 10. Here in my handwritten notes I didn't give any enumeration, but this we proved. Okay, so in particular, and that is actually the guy that we will use, the dual space. So remember that. So dual space of a normed linear space. So these are all bounded linear transformations from a normed linear space into the scalar field. That thing in our scenarios here, this is the field is either the real or the complex number field, which are complete in the absolute value complex modulus. So in our scenario, this dual space, all these dual spaces are always Banach spaces. Okay, so in particular, dual space is a Banach space when equipped with the operator norm. Okay, we already knew this, but I just wanted to write it down one more time. Okay, very nice. So now we had many examples. At this point now we will stop discussing examples, but we will now develop theory. And then once that theory has been developed, then we will go back to the examples and apply it to it. Okay, I'll see you in the next video.